Everything looks good on this end. Hopefully we got audio and video because we're ready to go. It's a little low on the audio level. I'm going to turn this up a little bit. So I'm doing a remote lecture today. We are visiting my wife's parents. So the first time we've gotten to come over their house and stay since the pandemic began. Exciting there. Kids get to see their grandparents. Wife gets to see her mom and dad. So that's why I'm out of the studio and on the road. Hopefully no internet glitches will kick up. This is an untested situation we got going on here. We've got fingers crossed. Boy, better lecturer, me now or me from the past? Well, I would say the better live lecturer is probably me in the past. At this point, it's been over a year since I've actually done a live lecture. I sort of lose my chops there. So I'm itching to get back up on stage and go for it. But we'll be back soon enough, soon enough. There we go. I'm checking out my stream health here. Yeah, I got one shot already. I'm gonna get my next one on the 13th of April, 12 days from now. I'll be past this, man. Hopefully, well, at least me and my wife. Still got to worry about the kids and, you know, the rest of the planet, but less worry on my own part. No, the Sax is definitely back in Ann Arbor. I'm over here in Grand Haven, so those of you who don't know our Michigan geography, Ann Arbor's over here, obviously. Grand Haven, way over there. I'm hanging out, ready to do this. All right, so today we're going to be talking about minimum spanning trees. And we got a nice picture of the United States there, and I believe this is one particular airline's route map. So you can see where we've got some hub cities there, and a lot of connections go out of one place to some places that are local. But clearly, this graph that we're looking at, which is a collection of vertices, these cities or airports where we land, and edges, the way that they're connected through these flights. This is a graph, but we're looking today to find a minimum spanning tree. And we'll define that by saying we're going to take some graph and find the subset of edges that make sure everything is connected, but we're going to do it as cheaply as possible. That's the general motivation behind the minimum spanning tree. We got 3 sections here. First, we'll make sure we're clear on what the MST is. Then we're going to go into a couple of different algorithms that you could use to calculate an MST. Right? We'll look at one for dense, that works well with dense graphs, then we'll look at another one that works well with sparse graphs. Well, that's what's approaching us. Here's our formal definition of the minimum spanning tree problem. We've got this edge-weighted, undirected graph, G, which has its vertices and edges. We're trying to find a subgraph, T, such that all the vertices are there. So you see that the V's are the same in the G and T, but what's different is the E and E prime. So E prime is a subset of E, such that all my vertices are pairwise connected, meaning that I can get from any vertex to any other vertex. There's no islands that are part of the graph but not connected to the main body. So we're trying to find some T that has all the vertices in there and all the vertices connected. And then the optimization piece is we want to add up all the weights of those edges in E prime and make sure that that's as small a value as I can possibly get. Minimal. That's our minimization. This is great. So if you think about how this should work, we're talking about connectivity. Everything has to be connected. If I see a cycle, that represents a redundant edge. I know that if I've got everything connected and there's a cycle, if I take out one of those edges, everything will still be connected. So that's what we're going to do anytime we see a cycle. And since we're trying to minimize, which edge should we remove from the cycle? Of course, the one with the highest weight. If we remove the highest weight edge, then we're looking at doing something that actually minimizes our tree. So if we see a cycle and remove the highest weight edge, great. We're looking for T to be a tree. That's why we said this is a minimum spanning tree problem. Now, to be clear, this is a graph algorithm. We apply this to a graph, but we're looking for an answer which is a tree. The important part about our tree is that we've got no cycles in there. Here's a small example of it. These are data centers in the United States, and they're color coordinated there. We've got Google's and Microsoft's and Yahoo's and Facebook's data centers. And these, of course, we would want to connect them as fast as possible. This requires laying fiber optic cable. And if you know about the United States, it's about 1,500 miles this way and about 3,000 miles this way. So there's thousands of miles locked up in here. And to put this buried fiber optic cable in, it costs about $1 million a mile. So we don't want to have any unnecessary connections. We like to have it fast as possible, and sure, there's going to be some redundancies in this system. That's the way that this is built up. But if we're talking about just general connectivity, we want to get everything connected, and to do this as cheaply as possible, we don't want to have any connections that are longer than they need to be. So this last year was a good year to take a look at Georgia. We're going to start in Georgia. You see that one over there, that red one is in Atlanta. And I'm going to jut out of Atlanta and just try to connect to something close. And you'll see as I keep connecting these data centers, I'm trying to use the least amount of digging and cable laying as I can. So this is how one minimum spanning tree for this data set might look. I did all of these by eyeballing them. So if you see something that looks a little hinky here, it's entirely possible. But this is close, and I think you get the idea. The idea is we want to connect everything. So I haven't made any redundant connections. There's no cycles in this tree here. And I haven't taken any unnecessary edges, like for instance, connecting that Austin to Denver up there. Is that just north of Denver? Like this yellow one down here at the bottom in Texas to that yellow one in the middle. That edge would be a longer edge than I need to connect those two items, because I can take a couple of 3 shorter edges and get more connectivity while also adding in the least amount of additional length. So that's the MST problem. Let's see how we might do it. Here is this nifty looking kite thing. It's got a total edge weight of 420. The minimum spanning tree says they have to be all pairwise connected, and then the sum of the edge weights is going to be minimal. So clearly, this has got more edges than I need in terms of my tree. If that's the graph, I've got more than I need because I can see cycles. ABD is a cycle, ACD is a cycle, there's a BCD cycle in there, ABC cycle in there. There's even a cycle from A to B to D to C, and so on. So let's just say, well, if I can remove the longest edge here, what if I take that 120 out? Well, that looks good. Everything is still connected. There's nothing that's completely isolated from the rest of the graph. That's good. Let's see if I can take my next longest edge out of there. That 100, that's pretty large. If we pull that, everyone's still connected. This is looking good. Let's keep that up. Let's take out that 80. Oh, 80 doesn't look so good. If I pull the 80, C is going to be completely isolated. So let's not do the 80. There's no cycles there. The only cycle that I see remaining is the ABD cycle. So if I'm going to remove something, it has to be from one of my cycles. Let's take the longest edge of my cycle. That's that AD edge for 60. And now you see that we have found an MST of this graph. There is no cheaper way to connect all 4 of these points that keeps all 4 points connected than this 140 edge weight, A to B, B to D, D to C. So that's an MST. We saw that we got to that one subtractively. We took all the edges and decided which edges to get rid of. So that's one way you could write an algorithm to do this. We'll look at a couple of different algorithms to do it. Right now, we're not going to get too deep into how we found that MST. We're just trying to make sure that we've defined what an MST is. And what's important to note is I can have more than one MST for a particular graph. Not this graph. This graph has no redundant edges that are of the same length. So if I show up to a particular graph where I've got two edges coming out of this vertex, say I go here for 30 and here for 30. If I can cut out one of these and come up with an MST, then I could probably substitute the other one in and come up with an equally weighted but different MST. So when we talk about MSTs and graphs, we don't talk about the MST for a graph. We talk about an MST for a graph. So there may be an existing minimum spanning tree. There may be multiple minimum spanning trees. But in order for them to all actually be minimum spanning trees, they all have to have the exact same weight. So that's what minimum means. It's the number that we can get to. So let's see if we can't think our way through some of this a little bit harder here. A little quiz, see if we can do some 203 style stuff. Does that feel like 203 already? Look at that. First word. Prove it. All right, no, it's 281. So we'll do a little bit of hand waving with our proofs and then we'll run away screaming. It's okay. So number one, prove that a unique shortest edge must be included in every MST. Think about that. I've got a unique shortest edge. How do I prove that that edge must be included in every MST? The second one, prove again. Prove that for the second shortest edge. Can you prove it? If so, how? Step three, what about the third shortest edge? How long can we continue along this route? First, we did the unique shortest edge. We did the second shortest edge. How about the third shortest edge? After that, we're giving these proofs a rest. So step four is show me a graph with more than one minimum spanning tree. I talked about it as a possibility. Now think about it and try to execute one visually. Number five, show a graph and its MST that avoids some shortest edge. This is a great time to do some exam studying. Let's pick up there. Look at that italicized words. This is how much I love you guys. I'm trying to make this easy. That italicized words there. Some is italicized. It's important there. Same thing here up in number one. It says prove that a unique shortest edge. Those two words mean a lot. When you're reading an exam, you need to find words like that and put some sense on them. So a unique shortest edge, what that means is there is one edge that is the shortest and there's no other edge of that length in the graph. That's very important to making this proof possible. Same thing here with this number five when we're trying to draw some shortest edge. That implies that there may be multiple shortest edges. You gotta see those things when you read them. We're trying to put as few words as possible on the exam just so that you can read it and get what you need and get done as soon as possible. There's not a lot of extra flowery language. So if there's a word there, it's important that you figure out why that word is there. Some shortest edge means that there's more than one shortest edge. Lastly, number six here, show a graph where every longest edge, see I italicized that one with my voice. It's not even italicized on the slide here. It says every though, that might be important as well. Show a graph where every longest edge must be in every MST. Wow, we're getting pretty intense here about how specific we are. So the more specific a question is, the more you should be picking up from that question. It's pointing you towards something with that specificity and or pointing you away from something with that specificity. So jump on that. All right, give you another 15, 30 seconds here to think through these, and then we're going to jump into them. I'll check the chat and see if I have anything unanswered. So last time I was just flying through lecture material, so I'm trying to just put a little bit more pausing in there and make sure I get this done at a reasonable pace. A little bit less material in this lecture anyway, so I should be able to squeeze it all in and breathe. All right, so how do we prove that a unique shortest edge must be in there? If you said proof by contradiction, you nailed it. So how do we prove by contradiction? We assume that what we're trying to prove is not true. Then we work our way back around to a contradiction, which then means that what we assumed at the beginning must not be possible. So if we're trying to prove that a unique shortest edge must be in the MST, let's assume that it isn't. So now I've got some MST that doesn't have the unique shortest edge in there. What if I add the unique shortest edge at that point? Well, I necessarily have now created a cycle, because without that last edge, if I had what I thought was an MST, it was a tree that connected everything, any one more edge is going to make a loop. So if I assume that I can create an MST without the unique shortest edge, then I add the unique shortest edge, now I have a cycle. I should be able to remove something from that cycle and still have an MST. So if I remove one of the longer edges from the cycle, not the unique shortest edge, now I'm back to an MST, but this MST has a lighter weight than the other MST, which I thought was an MST, and that's not possible. I can't have a lighter MST than another MST. That's a contradiction right there. So there's your proof by contradiction. If I add that shortest edge, it creates a cycle. I can remove some other edge, and now I get a new MST that's lighter than the previous MST, so clearly something was wrong. There's my contradiction. The same goes true, of course, for my second shortest edge. I can put that second shortest edge in there, and it must create a cycle as well. So as I remove something to fix the cycle, then I'll end up with an MST that's lighter weight than the one that I started with. And that's not good. So can I do this forever? Turns out I can't. When I get to the third shortest edge, the only time I can remove this third shortest edge is when it's in a cycle with the first and second shortest edges. Right? Only time I'm guaranteed to be able to remove it. Right? I may not be able to remove the third shortest edge all the time, because remember, it takes 3 edges to make a cycle. So if I've got the first shortest edge, the second shortest edge, and the third shortest edge in a cycle, then I can actually remove that third shortest edge and still end up with something that looks like an MST. So the third shortest edge is not guaranteed to be needed in every MST. All right, here we are. We're trying to draw a graph with multiple MSTs. Look at this unit square here. A to B, B to D, D to C, C to A. All of those edges have length 40. So if I wanted an MST, I could take just 3 of them, right? So it doesn't matter which 3 I pick. I could pick, in this case, AC, AB, and BD, or I could drop out, for instance, BD, and I could choose AB, AC, CD, and that would be an MST. Both of those have weight 120. Or if I wanted to cut out the edge AC, if I want A to B, B to D, and D to C, that would be 120 weight MST. So here is an example of a graph with more than one MST. As well, for answering number 5, it says some shortest edge is not included. In this case, all my edges are short. They're all of length 40, and if I have to make an MST by removing one of them, then I'm definitely removing a shortest edge. And it doesn't have to be quite this simple. There could be a graph with other edge weights. This one just has the one weight of 40, but I could have something with other edge weights and say, well, what if I remove one of those short ones? Will I still have a tree? Okay, we can see that on this next one. This answer is number 6. So here we see this graph, A to B for 20, A to D for 60, B to E for 30, B to D for 40, D to E for 30, and C to D for 80. That's my graph. I can not remove the longest edge. The longest edge here is an 80. If I take that 80 off, that D to C edge, C is completely isolated and it's no longer connected. So any MST I come up with has to include that longest edge. If there were more 80 edges, then things might be different, but remember we were trying to see if there was a way that I can come up with every MST includes every longest edge. And so I talk about multiple MSTs. Look at how that E is connected. E is connected to B for 30, and E is connected to D for 30. I could get rid of either one of those 30s and still have connectivity to E, but if I chose either one of them, they would still only contribute 30 to my ultimate weight. So if I want to get rid of my cycles, I'm going to probably take out that A to D edge, remove that 60, and then I can pick either one of those two E's. They will both give me different MSTs of that same weight. What is that? 170 if I remove the AD edge and either the BE edge or the DE edge. 170 would be my weight there. So there's some of it visually. And that's the minimum spanning tree problem. Hopefully it's clear to you now. Let's look at a way that we can actually do this with an algorithm, something we can code up rather than some lines and figures that we can point and gesture at, shout at. We're going to do this with Prim's algorithm. Prim's algorithm is a nice greedy algorithm that lets us find an MST. So we'll be talking about algorithm families and more about what it means to be greedy, and we'll recap that. But for now, we'll say that a greedy algorithm is one that always takes the best that it can. You can think of what greedy means. Greedy just wants and wants and wants. So in a greedy algorithm, if you take the best that you can get at any point, you don't settle for second best now because you know it's going to make things better later. You don't look back and see, well, I should have eaten that in the first place. Nah. Greedy is just greedy. Takes the best it can get right now and moves on. Next step, we'll take the best we can get then. Step after that, the best we can get then. So that's how Prim's algorithm works for us. As we look at the algorithm, we'll discuss it on the back end of it, but look for that greedy step. Where is it that we say, I'm taking the best, and I'm only going to take the best here? That's what greedy is. Prim's algorithm is going to help us find an MST on these edge-weighted, connected, undirected graphs. Obviously, we can't find an MST if something doesn't have connectivity. An MST without edge weights is possible. That's just any tree. But edge weights makes it something we can actually minimize. And it's good for undirected graphs here. We're going to work on graphs that have connections from A to B and B to A everywhere we see it. What it does is it greedily selects edges one at a time and adds them to this growing subgraph. So we start out the subgraph, we keep adding to it. We have this tree that expands. We grow this tree from a single vertex just by adding more and more edges. Here it is at a high level. We're going to initialize a tree with a single vertex. So that means we have to just pick some place to start. And it turns out that the way that Prim's algorithm works, doesn't matter where you start. You're going to get an MST. Different starting positions may give you different MSTs if there are multiple MSTs. But regardless of where you start, Prim's algorithm will give you an MST. What we do then is we continue to grow this tree by one edge, Any edge that's not already connecting might be something that I might want to add. So we grow the tree by one edge. The edges that are connecting the tree to vertices not yet in the tree, we find the minimum weight edge. So of all the things that are currently not connected to my growing MST, I'm going to take the shortest one, the closest one to my current tree. There's the greedy step. Right? Then we just repeat. We keep going on 2 until everything's connected. Find me the shortest remaining edge, use it. Find me the shortest remaining edge, use it. That's prims. So start with this graph G and 2 sets of vertices. We'll call them, for nicknames, innies and outies. Innies are nodes that we've already visited. So we can say these are the things that are in the set that is my MST, right? So we're going to start that out empty because nothing's in my MST. The outies are everything that hasn't yet been visited. So we're going to start with all of our vertices in there, initially all of V. We'll select the first innie arbitrarily. We'll call that the root of the MST. And arbitrary works very easily. We don't have to work hard in code to be arbitrary. So you think, well, what if I take a random number generator and pick the arbitrary index MST? That's way too much work. Just starting at the 0th one. How about the one at the beginning of the container? Because anybody could have put any point in any position inside the container, so the 0th index is just as arbitrary as anything else. So we start out as 0 as our root. That makes life easy. Then we repeat until there's no more outies. So every time we go through this loop, we move something from the outset to the inset. And we do that by choosing the outie that has the smallest distance from any innie, right? As I continue to grow this tree, more and more points get in the inset. And so it becomes easier for the outset points to be closer to the inset points because there are more inset points. When I start with a single inset point, there's only one way for every point to be connected to that point, which is through that direct edge. But once I've added 2 points, now a point here can be connected there, or it can be connected here. If I add 3 points, right, I can connect to either one of these things here. And so the more things that get added to the inset, the easier it is for my outset items to be connected. And so we've got to update to say, well, I want to know who every outset point is connected, is closest to. So when it comes time to take my next edge, I can always have that short pick. So every time through, I'm going to move something from an out to an in. And I'm going to do that, of course, the times, because I want to make sure that I've got everything in the inset from the outset. We got one implementation issue that is, as I'm trying to find that edge that's the shortest, how do I do it? One way to do it is with a linear search. I just look at all remaining points and say, hey, how close are you? If you're the closest, we're taking that. So that's my linear search. Another way to do this is to take each edge that I've discovered and slap that into a priority queue, where I've got a min priority queue saying, what I want out of here is the shortest edge that you know about. And that just keeps firing me shortest edges. If that edge represents something that doesn't create a cycle, then I put it in the tree. If it creates a cycle, I just throw it away and get another shortest edge. So we'll look at that if that's not as clear to you. It's just a way to modify one aspect of the algorithm, that how do we determine the next edge portion of it. To get this done with either the linear search or the priority queue version, we're going to come up with this data structure that makes things happen. We need to have 3 pieces of information about every vertex. The first is what we call case of V, and that K is short for known. Is there a way that we know how to connect this to the tree? If we don't know how to connect it to the tree, we're going to say it's false. We don't know this, and that's how everything starts, because nothing's connected. False. We don't know how to connect it to the tree. Then there's d sub v, which is the distance. What is the length of the edge that connects this point to the tree? And we're going to keep trying to minimize that. That's where minimization is. So when we're trying to minimize, we're always going to start with our values high and then keep cutting down until we get to what we want. So we're going to initialize this with a bunch of infinities, right? If we're using floating point values, which normally you will if we're talking about 2D coordinates here, then we'll start with an infinity. If you're doing something else and you know that you've got integer types, you can use a max, but we're generally going to be using infinities there. And then lastly, this piece of V. This is a vertex that precedes or is the parent of, whatever it is when I say this vertex has a distance of X to the tree, well, that means that that distance is between the vertex and some other point. This piece of V is that point. The piece of V is the one who brought you into the gang, right? The one that connected you to the tree, that's your connection to the gang. That's what the piece of V is. So we need those 3 points for each vertex. And I could do this with 3 separate vectors. It would work. The algorithm would have the same overall time complexity. A slightly faster version of this, however, would be to say, rather than having parallel vectors, and we call them parallel vectors because each of the 3 vectors represent information about the same object if I go to the same index in a different vector. However, we know from the way that our processors and caching works that you would go faster if you had a single vector that had a data structure in there, and each one of those data structures had those 3 items. So, better way to do this is not 3 vectors. 1 vector. Put classes or structs in there or whatever. Some object deal. So here's Prim's algorithm in pseudocode. Be very careful about this. I feel like we're deep enough into 281 that everyone is intensely stressed out at all times about time and memory. And while it's something to be concerned with, it's not something that you should live and die over, right? So that means don't get too hopped up on it. Take this algorithm as it is. Implement it that way. If you try to get tricky with it, you might cause yourself more problems than you actually save. So here's how it is. Like many of our algorithms, we've got some initialization that we have to do. Then we're just going to jump into some loop and we ride that on until we hit the sunset. So start out by setting the d sub v of some point to be 0. You can pick, this is the point we pick arbitrarily. You pick that point and you say, well, now your d sub v is 0. If you remember from the previous slide, we said that all the d sub v's start out as infinity. So that's the only thing you have to update, set d sub v to 0. Then we go through this loop here. This loop runs v times, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Goes v times, because every time through, we set one of those k sub v's to true, and so we have to go v times so that we can set all v of those k's to be equal to true. Step 1 in the loop, from the first set of, from the set of vertices for which k sub v is false. I'm looking at all my falses and trying to find the shortest d. That's what that says here in many more words. Look through all my falses, find the shortest d, right? Look through everything where k sub v is false and see what is the value of d sub v there and minimize that. So if you're remembering, we started out with all of our d's as infinity. Great. The one we're going to find, this one, because we set one of them equal to 0. Let it be, right? So we loop through. This is our linear search. Look through all of those things. Find the shortest one. That's the end of step 1. Step 2, mark it as true, because we now have found something that's got its shortest connection. We mark that as true, and then step 3, what we're going to do is go to every vertex that's adjacent to the point that we just chose. Everything that's adjacent to this v, right? That vertex that we chose, all of the vertices w that are adjacent to v, we're going to go through and see if they're false. Test to see if the distance from v to w is shorter than the distance that's already in the table. That's kind of an inversion of what's written here, but it means exactly the same thing. So It says test whether this adjacent point d sub w, that's distance, test whether the distance that's already in the table is greater than the distance from this new point v to that point. So if the point that we've just chosen here is closer to w than what's in w's row in the table, what we're going to do is update w's row in the table and say, well, your new distance is this v comma w, the distance between those 2 points. And since v was the one who has now connected w, we're going to set p sub w equal to v. Let's check the table. All right. So this is our warning slide here, and I've already issued this warning. I get to put it in a slide and reissue it. Don't mess around with this algorithm. Do it like this. Just do it like it said. Exactly the way that slide said do it. Do our outer step, then steps 1, 2, 3. In a loop, get it done. Right? It doesn't say, let's set the first vertex equal to true outside the loop. Because, hey, I just set it equal to 0. I know that that's the closest it's going to be. So I could just set that to true now, right? It makes the algorithm harder to write. Just do it as it is. What you're trying to do, if you say, well, if I set this equal to true outside the loop because I know I just set it to 0, you're trying to save yourself from doing V work in a V squared algorithm. Who cares? It'd take 10,000. We have 10,000 vertices, and what happens when I square that? I get 100 million. So you're thinking, if I can save 10,000 work out of this 100 million, it's going to make my algorithm so much faster. Pro tip, it ain't. 10,000 off of 100 million is negligible. It's not even noticed. So don't get tricky, because when you try to reorder this algorithm to get tricky ahead of time, I can't tell you how many hours I've spent in office hours helping somebody fix something when they got too tricky too soon. Trying to fix this before you know that it's even a problem is premature optimization, and premature optimization is horrific. Just write it, make some good choices at the beginning, get it done. Test it, make sure that it works. Verify that it works everywhere, and then check to see, is it good enough? Because if it is, you're done. There's no sense trying to make this absolutely 100% awesome. From every semicolon that I write, this is the best possible code that exists. That's not the way real coding gets done. It's not the way that it gets done. You write something that works, and then you go back and refine as necessary. And we don't have to do that much refinement in 281. We're not writing inner search loops at Google or stuff in the Linux kernel. Just writing some 281 solutions here. So don't try to get too tricky. You'll only make yourself sad. So here is my graph. And I've already taken my first step, and this is the step that's outside of the loop. You see that I've set d sub v equal to 0 for something. Great. Let's breathe that graph in over there. What do we know about this? We know A to D is definitely in the MST. Why? That's the shortest edge. We've proved it's going to be in there. How about E to F? Also a second shortest edge. We know that's going to be in there. Then as we move to that third shortest edge, CE, well, it doesn't create a cycle with that AD or EF edge, so turns out that one's going to be in there too. You can pretty easily, by inspection, figure out what this is going to be before we Prim's algorithm it. And that's great, because then we know what the right answer is going to be, and we can verify that we've done Prim properly. So if you look at this, you see that we can add the 1, the 2, the 3 edge in there, the 4 edge even, without creating any cycles, so they'll all be in there. Either one of those 5 edges, C to D or D to F, is going to create a cycle, so neither of them can be in there. After that, the A to C edge for 8 is also going to create a cycle, so that's not going to be in there. I haven't found a way yet to connect B, so I'm going to take the shortest of the 2 remaining edges, and that's the AB edge. So my MST ahead of time looks like A to B, A to D, D to E, and then E to C and E to F. That's my MST. Hopefully Prim's gets it. So we'll start out by picking our tree root arbitrarily. In this case, we're just going to pick the first thing in the vector. It's A. So A is my first one. I'm going to set its distance equal to 0. Now I'm ready to jump into my main loop. My main loop is going to go these 6 times, trying to mark each one of these things true once through, right? So the first thing I do in my big loop is I go through all of the falses and find the one with the shortest distance. Bing, 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 bing. Yeah, it's that one. It's A. So step 2 is let's mark K sub V, or K and A, equal to true. We mark that equal to true. And then the third step is we go to everything adjacent to A. In this case, B, C, and D all have edges that connect back to A, which makes them adjacent. So I go to all of them and I update their distances if possible. So we see it here. It's changed color here. It's in red. It's 13, 8, and 1, whereas before they were all infinities. So 13, that's less than infinity. I would approve a choice of 13 over infinity any day. 8, less than infinity, ditto. 1, less than infinity, ditto. So I can come back into my table and say B's distance is now 13 when connecting through A. So I put A in the P column. C's distance is now 8 when connecting through A. D's distance is 1 now connecting through A. So that happens in my step 3. I go through there. And that's it. My main loop is done. I'm going to go back and do the main loop again. Remember what the main loop says. In step 1, find any one of these vertices whose K sub V is false and get the closest one, the one with the shortest D sub V. So I don't check A anymore because it's already marked as true. So I'll look at B, say, well, 13, that's a great place to start. I haven't seen anything better than the 13. I'll take that. Oh, wait. There at C, I see an 8. That's better than 13, so I'm thinking I'm going to go with that 8. That sounds great. Oh, what about this D? I can get there in 1. That's even better. I'll take that until I see something better than 1. Well, infinity no better, and we're done. So now, after step 1 of the second iteration of the outer loop, step 1 has determined that vertex D is the closest one. So let's mark that as true, and then update everything adjacent to D. Right? D is adjacent to A, C, E, and F. A is already marked as true, so we don't have to update that. Can we make that trip shorter? Before I got here, that trip was 8, because I was coming from A. But if I go from D to C, I can get there in 5. That's an improvement. So I update C's distance to be 5, and its parent to be D. Right? Then what else is D is adjacent to E, which had as its distance infinity, so I'll take that 4 over infinity every day. Same thing with F, that was an infinity as well. So I'll update those two with those edges from D, the 4 and 5 on E and F, and set both of their parents to D. Great. In the graph, you can also see that A and D are connected now with a hard edge. We know that that edge is included. So those other dotted line edges, those are the edges that exist in the graph, but might not necessarily exist in the MST. We know that bold edge connecting A and D is really in the MST, so it's there. Oh, I got ahead of myself, sorry. Let's do step 1 again. Step 1 says, look at all of my falsies, find the one with the shortest D. B is a 13, looks good. C is a 5, that looks better. E is a 4, that looks even better. F is a 5, not better. Let's go back to E. That's the one. Let's mark that one as true and update everything that's adjacent to E. What's adjacent to E? C, D, and F. Well, D is already marked as true, so we don't really care about that. But C, which had a previous distance of 5 through D, can be updated to a 3 from E. That's an improvement. D was already marked as true, so we leave it alone. And F had a distance of 5, but now this improvement from E to F in 2 is better, so we'll update F's distance to 2 and set its parent or its previous to E, because that's how we get that 2. There we go. That's the third step in the outer loop. Again, we just keep this going. Remember, the outer loop, every time we've gone through the outer loop, one of these has been marked true. So I've got to go through that outer loop 3 more times and I'll be done. All right, I start out again. Let's start at the top. There's a false. 13 looks good. 3 looks better. 2 looks better than that. So I'm going to set my current vertex to this F. I'm going to mark it as true and then update the things it's adjacent to. But once I mark F as true, you'll see that it's only adjacent to D and E, and both of them are already marked true. So in step 3, I don't do anything in this particular iteration because nothing that F is adjacent to is still false, so I don't update it. All right, what's left? I've got to get another edge here, right? So I will go back and say, how about B for 13? Looks good. C for 3 looks better though. There's my current node. Let's update that one, mark it as true, and we've connected that one from C. We marked it as true because it was connected to E. We see that its distance was 3 from E, so that's the line that I harden on my graph, that C to E edge. C was adjacent to A, B, D, and E, where A, D, and E were already marked as true. The only thing that I could have possibly upgraded was the B connection. And since CB is 15, and the shortest I had on B was already a 13, I don't update that, because C is not an improved way to get to B. It does not beat the way that I get there through A. So we keep that one. The next up, I'm just going to select B because it's the only falsy at this point. I can mark it as true, which of course means that I bring in the B to A edge because B's previous was A when I marked it as true. So there's the MST that we picked by inspection, and the algorithm has calculated it as well. That's Prim's algorithm. All right, here's your chance to run some MST. Got a nice table here for you. K sub V, D sub V, P sub V. It's got these 5 vertices, A, B, C, D, and E, and this simple graph that connects A and B for 1, A and C for 3, B and C for 4, B and D for 6, C and D for 5, D and E for 2, B and E for 7. So take this and turn this into an MST. Before we get started, if you want to do the quick inspection thing, it's always fun. What do we think the answer is going to look like? Well, we know the first shortest edge, AB, is going to be in there. We know the second shortest edge, DE, is going to be in there. And we can tell that the third shortest edge, AC, doesn't create a cycle with those two, so it's going to be in there as well. So we've already got 3 of the 4 edges we know that are going in there. What remains then is, how do I get that last edge? It looks like the 4th shortest edge, BC, would create a cycle, so we're not going to put that in there. The 5th shortest edge doesn't create a cycle, adds connectivity, turns into our 4th overall tree edge. Done. So B to A to C, C to D, D to E. That's what it's going to be in the end. Use prims. They give you about 30 seconds to get this done. I know we would love more time. It's hard to really gauge this without seeing faces in a lecture hall, but give it a shot. Check and chat. All right. Well, let's get back at it here. If you're still primming, I apologize. You will get to where we're going to get. I'm just going to go there in one step. This is what my prims table looks like when I get done. We already knew what this was going to be. We figured out by inspection that it was going to have the 4 edges that we chose. A to B, A to C, C to D, and D to E. And what I've got over here is my prims table. See that I've added values in there and crossed values out that I've updated, so you can kind of see how that went. Because now I want to talk about something vitally important to all 281 students, and that is the final exam. This was a really straightforward prims problem. We could see ahead of time what the answer was going to be. We could just by inspection figure out what that's going to be. So then, does that seem like a reasonable type of test question that I would give you something where I'm trying to figure out what you know about prims that you could just solve by inspection, whether you knew prims or not? That doesn't sound like a good idea. So if I was to give you a graph like this, I wouldn't say, use prims to tell me what the MST is. You could just look at it and do it. Okay, so that doesn't give me a good way. So you say, it's easy enough to do this by inspection because it's such a simple graph. Great, so then would I be able to give you an exam where I say, well, here's this graph with 47 points on it. Now use prims in the 2 minutes that you've allotted for this multiple choice question. That's not going to be fair either. So one's too easy, and it doesn't actually answer whether or not you know what I'm asking if you know. The other one's too hard because there's just not enough time to get that done. So somewhere in between there's got to be a way for me to ask whether you understand prims, right? If I give you enough in the question, here's the graph, I would have to say something like, start your prims at index A, because if you start at a different index, you would get a similar MST. In this case, since there's only one different MST, you would get the exact same MST, but you might have some slightly different values in the table over there. So how do I know if you know what I want you to know? Think about that. Try to write a question here. So well, what can I say? If you knew how to do prims, and I said, here's the thing, what is the P sub V of D? Options are B, C, E, none, 2 of the above, none of, I don't know, something like that. But that's a good way to write a multiple choice question. If you understand how prims works, then you would say, well, D's parent would have to be C, because that's the way that it got connected. It didn't get connected through E if I started at A. So that's something they can do. As you look at this prims table, once we're done, it's important to note that you can see the edges that are in the MST by looking at the table. We see that there's going to be one less edge than there are vertices. That's what keeps us tree. It keeps us out of cycles. So there's got to be V minus 1 edges. This first one here, that A that goes from A to nothing, that's my deleted sort of edge-like thing. But the rest of those things, we can see in the second row, B's parent is A, which means the edge AB is in the tree. Same thing with C's parent is A. That means the edge AC is in the tree. And we see that there with the 1 edge and the 3 edge. D's parent is C, so the CD edge has to be in there. And we see that 5 down at the bottom. And lastly, E's parent is D, so the DE edge has to be included in the MST. So once I get done with prims, everything I need to know about this MST is in this table. All of the edges that are included. I also know the total weight of the MST. If I just add up that entire D column, you'll see here that I get 11. That's the total weight of my minimum spanning tree for this graph. So I can take prims, run through prims, calculate that, subtotal that D sub V column. That's going to give me my minimum spanning tree weight. And any of the edges that I want to know that are in there, I can take every point but the first point, whose distance I set to 0, and look at its parent, and that will tell me an edge that's in the graph. So, as you're looking at this, we see what the answer is. We've figured out how to find it. Now, spend some time thinking how to write from this simple example right here. Find a way to write 3 exam questions, multiple choice questions, that can only be answered correctly if you understand and can successfully apply Prim's algorithm. That's one way to get this exam studying done. So, there you go. Chew on that one, study that. That's how you get there. Let's look at complexity. With my linear search, remember, here is my pseudocode for Prim's algorithm. We're going to repeat until every case of V is true. So that means we're doing this outer loop V times. Inside the outer loop, I've got these 3 steps. The first step is for all of the vertices for which case of V is false, find the one having the smallest tentative distance D sub V. So I've got to do a linear search, look at them, and that's going to be me looking at all of them. So there's a big O of V right there. I set the case of V to true in step 2 after I've found the shortest one. That's a constant amount of time. It's easy to mark something as true from false. Constant time. Then for each vertex adjacent to my current vertex, for which that K is false, test whether its distance is greater than the connecting distance. If it is, update the distance to be this new shorter distance and set its parent. How much time does that take? Well, how many vertices W might be adjacent to V? In the worst case, all of them, all V of them. So I'm going to say that the most that any vertex is going to be big O of V, and the cost of doing each one of them is a constant amount of work. So I've got the worst case of V here at step 3. So this outer loop happens V times. This is about V work, constant work, V more work. So V work, V times V squared. All right. Here's how it will work with a heap. In a heap, what we're going to do is every time we discover a new edge, we're just going to push that edge into a heap, a priority queue, if you will. And that priority queue is going to be a min heap that shoots out my smallest remaining edge. So in this way, I don't have to do that linear search, but I do have to do that logarithmic insertion into the table. And then once I pull something out of the table, I've got to do a logarithmic fix. It's important to note here that I don't want to use a heap all the time. When would I use a linear search, and when would I use a heap? Well, if I were to insert everything into the heap, we know that those are big order, a big O of log E. These are the edges that I'm inserting in there. If all the edges are in there and I insert the last one, on average is about a log E insertion. And since I'm inserting all of them, it's going to be like E log E to do all these insertions. So then the question is, if I know that the linear search version gives me V squared, and these insertions into the heap give me E log E, when? When is V squared better than E log E? Density. The density of the graph matters. In a sparse graph, E is like V. So when you want to compare V squared and E log E, if E is like V, you're looking at V squared versus V log V. I'll take the V log V, thank you. What happens if I've got a dense graph? In a dense graph, E is like V squared. So now you're comparing V squared to V squared log V squared. Well, v squared log v squared is the same as v squared log v. You can just take the square out of the logarithm, but it's going to be v squared times something more, or just v squared. So in a dense graph, the linear search version at v squared is more efficient than the heap version at v squared log v. But in a sparse graph, the linear search version at v squared is slower than the heap version, which is e log e, or in that case, v log v, because we're sparse and e is approximately v. So that's how we can make our distinction between the two of them. This is just walking us through the prim heaps version. See that we're initializing n to be the number of items in d, that's constant time. We're going to create a table of size n, so we're going to have to run through all of the things and set their k's to false, set their d's to infinity, and clear their parents out. So that's going to cost me v in the create table step. An empty heap, I can do that in constant time. It's just like, it's there, nothing in it. Set the initial distance here of my root to 0, constant time, and insert that thing into an empty PQ, which is going to happen in constant time. So here's my initialization step. Now I've got to go through some loop. And here's my outer loop while, and all of the things that I looked for in there are here. As long as my priority queue is not empty, I'm going to get the edge that comes out that's shortest. Get min. This next step is a little unclear without seeing it. It says, if that thing that I just pulled out is not known, how could it be known already if I just pulled it out of the table? Well, if I've got two ways to connect to some vertex, so let's say I've got A to B and C to B. When I start at A, I'm going to insert the AB edge into the heap. At some point when I'm at C, I'm going to insert the C to B edge into the priority queue as well. So now there's an edge that exists in the priority queue, AB, and the one that exists in there, CB. One of them is shorter. Doesn't matter which. That one's going to come out first. So if AB comes out first, I say, okay, we now know how to get to B. We'll mark B as true. Later on, because it's such a longer edge, when CB comes out, I say, well, should I put the CB edge in there? No, I don't need to, because B is already marked as true. So that's where that comes in here. That's where we say, if there's no connection that's known already, because I just pulled an edge out, that edge might be redundant though. So if the edge is redundant, you see that this if just throws it away. If it's a redundant edge, we do nothing. We go on and get the next edge. That's it. If the if fails, the next step is go back to the top of the while again. If the if succeeds, then we've got something that's not known, and we have necessarily to update an edge in this prim's table. So we're going to mark that thing as true, because now we know that's the one that we want. And then for every vertex adjacent to that vertex, we're going to calculate its distance. And if that distance is less than what's already in there, then we update the distance and update the parent. And we're going to insert that edge into my priority queue so they can come out later as necessary. All right. That is, I said mark that as true. We don't mark it as true, sorry. We don't mark it as true until we get back here. When the thing comes out of the priority queue, that's when we can mark it as true. All we're doing here is updating the distance and updating the parent for that edge. We insert that edge into the priority queue with its distance so that it comes out in small distance important order. As you look at each one of these things, they're all pretty mundane constant time stuff, except for PQ insertion. That's log E in the worst case, because there's E edges in there. And in the worst case, I've got this PQ as a big O of log E to do my insertions. How about this? For each thing adjacent to a particular one. So now you can see that we're doing this 1 plus E over V. Memory serves, you know that we're talking adjacency list now. You know that we're talking sparse graph now, because adjacency list is where we get to 1 plus E over V, and we only get to adjacency list when we're talking sparse as well. So that's a dead giveaway there. That's how Prims works. You can use it on dense or sparse graphs. It is much more effective on, it's much more often used, I should say, on dense graphs. There's a way to get Prims to work for us on sparse graphs. There's other sparse graph algorithms as well. So here's my complexity. It's about the same. I've got this outer loop that happens v times. I've got this selection of vertices. Now, when I select the one that's the closest vertex, I can just take the top of the priority queue off. I can get that in constant time, but when I take the top of the priority queue off, I break it. I gotta fix it. That's gonna be this log E or log V, which is the same when we're talking heaps, because we're only doing this when E and V are the same. So log E or log V there. So I would only do that step one in log V. I can mark this as true, that's fine. I've got this thing here, which is a lot more complicated as well. For everything adjacent to a particular vertex, now since I'm using an adjacency list, I can find this directly because I just go through that list. So the most at any vertex could be all of them. The cost of each one getting put in there is of course log V. But one thing to note is that we only visit every edge once over all the iterations. So I'm not going to end up with all of them in all of them. By the time I get done with all of my loops, I will have seen all of my edges, however, though. So since every edge is visited once, I'm going to put that in there just the one time. So since my outer loop goes v times, I end up with something here that looks like v times the biggest thing from 1, 2, and 3, and it looks like I'm looking at a log v in there. So I end up with e log e or v log v, if you want to call it that with heaps. When I'm doing the simple nested loop with the linear search, that's v squared. And so here's where your thought comes in there. I'm talking about PQ, dense versus sparse, what goes there. All right, that's Prim's algorithm. We saw it greedy. We saw it work with linear searches. We saw it work with priority queues or heaps. Both ways to get to the edges that I want. Up next, Kruskal's algorithm. Now this is another way to get to an MST. This is also a greedy algorithm. See if you can figure out where the greedy step is. Remember what greedy is. Greedy says, I'm going to make a locally optimal decision. Not thinking backwards or forwards. I'm thinking right now. What's the best I can do right now? I don't think about, well, if I do this a little soft now, I'll be able to get stronger later. Or if that was a bad decision earlier, maybe I'll do something a little bit now to mitigate it. Greedy is like, best now, let's do this. Kruskal's algorithm, find me an MST, not the MST. Find an MST on an edge-weighted connected undirected graph, similar to Prim's. This is going to greedily select edges now, one by one, and add to a growing subgraph. We were doing edge work obviously previously in Prim's, but we were doing that through the lens of find me the closest vertex. Find me the closest vertex out here and bring that back to me. That's how Prim's works. Kruskal says, well, let's just look at the edges. I'm going to take these shortest edges because we already proved that the shortest edge must be in there. Second shortest edge must be in there. Third shortest edge would be if it doesn't create a cycle, so let's extend that. I'll keep adding in the third shortest edge and fourth shortest edge. As long as they don't add a cycle, I'm going to add that edge. If it ever does add a cycle, we just throw it away and get the next shortest edge. Lastly, since I know there's going to be v-1 total edges, I could be a little adaptive in this one. As soon as I've added v-1 edges, let's just stop. There's once I've added v-1 edges to my MST, I've got an MST. Anything else that I add creates cycles and is less optimal, so we could stop early if we want to. Kruskal's differs from Prim's. In Prim's, I would pick a unique root, arbitrarily, but unique. I would pick a single root and then grow the tree by connecting new things to that over and over again. In Kruskal's, what I'm going to do is just pick the best edges I see. Hey, there's a good edge. I'm taking that one. That one over there looks pretty good. Taking that. As long as it doesn't create a cycle, I just keep adding edges. As soon as I pick up an edge that's too close to too many other edges, I can say, well, that one creates a cycle. Throw that away. Let's check the tape. Step 1 of Kruskal's algorithm, pre-sort all the edges. Now there's another dead giveaway. Look at step 1 there. Pre-sort all the edges, which is of course E, number of edges, big O of E log E. And this is just sort. I mean, get yourself a good sort. Quick sort, probably. Intro sort, you know, if you're feeling cool. Something that's going to give us an optimal sort is going to be E log E. Pre-sort all the edges, E log E, which is approximately E log V. When is that? Only when E is approximately V. So, Kruskal's algorithm, yeah, that's a sparse graph algorithm, right? So pre-sort all the edges. And then what we're going to try to do is insert them in order of increasing weight. So this is a decreasing sort. I said that backwards. It's not a decreasing sort. It's an increasing sort. We're going from small to big. So we're going to try to insert them in order of increasing weight. That's what step 2 says. Any edges that create cycles get thrown out. So initially we find out that our edges may be disjoint. Like I said, I could find this shortest edge over here, I said a second shortest edge over there, and there could be no connection between these 2 points, no direct connection between any of these 4 points. And that's fine, because as I add more edges here and there, eventually my trees grow together, right? So I say that Kruskal's grows a forest, a bunch of small trees, and eventually those trees connect up into one big mother tree, and that's our MST. So here is a familiar graph. We just did this. So we know exactly what this looks like. I've got the AB edge, the AD edge, I've got the DE edge, EC edge, and the EF edge. That's going to make my entire MST of this problem. So let's apply Kruskal's. Kruskal says, well, if I sorted all of these edges, I would definitely take that 1 edge. Next, I would take the 2 edge. And these things are colored differently just to highlight the fact that they are currently not connected. When I said that we're going to grow a forest of trees, I have a teal tree that connects A and D, and I've got a blue tree that connects E and F. But they are so far distinct trees. As I add my next shortest edge, that CE edge for 3, that extends the blue tree, but we still haven't connected. Now, the remaining shortest edge is what? That length 4 edge connecting D and E. So when I add that, it does not create cycles, but it does merge my 2 trees. I had a teal tree and a blue tree. Now there's only 1 tree. It's the teal tree because so far those 2 trees have merged together. And there could obviously be more in a much larger graph. There could be hundreds of small trees when you start that eventually coalesce into 1 tree. So we start out with all of these indistinct points, these disjoint sets. I start out with n disjoint sets of size 1, and I want to end up with 1 set of size n. That's union find. So last up, as I look through the rest of my sorted edges, I've just added 1, 2, 3, and 4. I would pull out a 5 edge, which would either be DC or DF, doesn't matter which. I would get a 5 edge and say, hey, that 5 edge creates a cycle. I'd get the next 5 edge and say, hey, that 5 edge creates a cycle too. Both of those get thrown away. Then I get the 8 edge from A to C, but guess what? That creates a cycle too. Let's throw that one away. And what comes next out of my sorted container of edges? That AB edge for 13. Once I add the AB edge, that is my 5th edge. I'm done. There's only 6 vertices. So the 5th edge finishes me up, and I'm good with that. Also, if I was to continue, I would only have 1 more edge in the container. That would be the BC edge for 15. And if I've included the AB edge, adding BC just makes a cycle, so I would still have to throw it away. That's Kruskal's algorithm. Visually, we talked through it, and we know what the MST for this particular graph ends up being, and so this is trying to do that. Let's do the complexity analysis here. It's pretty easy. We've got to sort this. We've got to sort all the edges. E log V here, and we know why we call it E log V. It's the same as E log E because we're only doing this when we're sparse, when E is equal to V. So we'll call this E log V, and that's why we call it E log V instead of E log E. It's just a tradition in the way that this type of algorithm gets evaluated. We put those V's in there. So this is E log V, but you know that that's the same as E log E. It's even the same as V log V. The literature generally discusses this as E log V, just so that you know that why there's a distinction there. There's a distinction without a difference. So after I've done this, which turns out to be the slowest part of the algorithm, that's the E log V to sort all of them, then all I have to do is loop over each one of my edges and decide whether or not I'm going to throw it away, which I can do in constant time, or I can add it, which I can also do in approximately constant time. So most of the time I end up spent testing for these cycles. How do I test for cycles? That was what union find was all about. Turns out that it takes very little time to do so if you do union find properly. This should be a familiar slide. We used this back in the early part of the semester. We talked about union find. We talked about these n locations with no connecting roads on Mars, perhaps. The roads get added one by one. For now, we don't worry about the distances. We're just trying to see if there's connectivity. We want to connect these cities as soon as possible. Redundant roads slow us down. So this was our disjoint sets problem. And just as we said then, this awkward union find kind of thing is going to be important for many things. This happens to be one of them. How do I find this minimum spanning tree? I need union find to do it. So we're running low on time. We're going to power right through this. Another familiar graph. We've got this 5 points graph A, B, C, D, and E with our edges 1, 2, 3, 4, 5, 6, and 7 that connect them. And we know from previous example on this exact same graph, we're going to end up with the AB, AC, CD, and DE edges. We could see them, the 1 edge, the 3 edge, the 2 edge, and the 5 edge. Those are going to be in there. But let's do this with Kruskals and go. For starters, I need to sort all these edges. So I'll sort them, and that fills up my table over there. You see that I've got my shortest edge, my weight 1 edge is AB, the 2 edge is DE, 3 AC, 4 BC, 5 is the CD edge, 6 is the BD edge, and 7 BE. So now I've done the hard work. That actually took me E log V time. That was slow. Down here at the bottom, I've got my union find table, which is just these 5 locations because there's 5 vertices. And each one of these vertices needs to know who its representative is. So in some container, I would say each one of these 5 vertices is represented by its representative. We start out with n disjoint sets of size 1, so everyone is their own representative. So in my union find vector, I've got A, B, C, D, and E representing A, B, C, D, and E. Now I just go through my table of sorted edges over there and try to insert them as long as they don't create a cycle. So the first up, I get this edge A to B, and the question is, I would like to add the edge AB, but it's important that A and B are not already connected some other way. This is where find of union find comes in, because adding the AB edge is the union part. So I find A's representative, it's A. I find B's representative, it's B. Great. That means they're not already connected. That means that I can add that edge into my MST. And so that's what I get here. I do that right away. And I'm also going to update. You'll see that B's representative got updated to A. B is represented by A is represented by A. Therefore, I've got the AB edge as something that's marked part of my MST. Up next, the DE edge. D is represented by D, E is represented by E. That is 2 unique representatives. I can union those 2 things, so I say, yes, there is my forest of trees starting to grow. I've got an AB tree, I've got a DE tree. Up next, the 3 edge, A to C. A and C have different representatives. A is represented by A, C is represented by C. They can be connected. I do that. I move on. A and C are now connected. I set C's representative to A. So now A, B, and C all have representative A. D's still representing D, and E's representing E. So there's my two trees. The next edge that comes out of my sorted collection of edges is the 4-weight edge. That's the one that connects B and C. B's representative is A, C's representative is A. They have the same representative. I can't add that edge without creating a cycle. I have no need to add that edge because they're already connected, because they have the same representative. So I take that BC edge and throw it away. Up next, the 5 edge connecting C and D. C's representative is A, D's representative is D. They've got two different representatives. I can union them. I put that edge into the graph and I'm done. If I want to be adaptive, I can see that with 5 vertices and 4 added edges, I'm done. I can, however, continue just as well. To prove how this union find works, you look here and you say the next edge that's coming out is the BD edge for 6. B's representative is A, D's representative is A. They've got the same representative. Edge gets thrown away. Lastly, as I go to the 7 edge from B to E, I see B's representative is A, E's representative is D, but is it really? If I say E's representative is D, D's representative is A, A's representative is A, so in reality, E's ultimate representative is not D, E's ultimate representative is A, and B's representative is A, so there you have it, they're already connected. If I were to do this, I would hopefully be using path compression. What that means is when I do the find on E says, who is your representative? E says, I think it's D. D says, I think it's A. A confirms, yes, it is A. Then as I come back out of that, I make sure that D's representative is marked down as A. I also make sure that E's representative is marked down as A as well. That's the path compression, because the one find to figure out who E's representative is updates E's representative to be that ultimate representative. So you'll see here the path compression here has updated it so that E's representative is A. Since B's representative is also A, I've got an edge that is only going to create a cycle. We pitch it. That's Kruskal's algorithm. We'll answer some more questions about this here probably in office hours. Rewind the vid and see what makes sense. If you need to work through some of these things, pick a graph and use either one of these tables to make it happen. Use a Prim's table with a K, D, and P to write a Prim's algorithm. Use a union find table in a sorted container to do a Kruskal's algorithm. Make sure that you can do it. And as before, when I talk about how do I study for these things, hopefully I've done my job and I've explained this in a way that makes it look crystal clear and dead simple. That's what I do. That's what I do. I just make things look simple. But what does that matter to you if you can't get the grade you want? And you get the grade you want by being able to being able to answer questions. So if you listen to this and it seems like, okay, I get that, go back and say, if I get it, how can somebody ask me a question that really proves whether or not I do? Work through an entire Kruskals and look at different points during the Kruskals where someone who didn't know how to do it might not get it done. That's a good place to ferret out where an exam question comes from. They sneak out of those little cracks where someone who doesn't quite understand the algorithm kind of waves their hand and hopes that the picture is clear enough to get the right answer. Yeah, that's not going to work when we're talking algorithm questions, because algorithms are only really good when there's so much data you can't see a picture of everything. So keep that in mind, and this is how you should study for this stuff. Remember that our MST is this lowest cost subgraph that includes all the nodes and keeps everything connected. We looked at these two greedy algorithms. We looked at Prim's algorithm, which keeps finding new vertices to add, and we looked at Kruskal's algorithm that keeps finding new edges to add. both of them end up getting us to an MST. And if you were to perform a Prim's algorithm and a Kruskal's algorithm, even on the same graph, regardless of how well they worked efficient time-wise, you would still be getting an identical MST. We want to use for our dense graphs, we're going to use the nested two-loop Prim version. That's the outer loop that runs through all the vertices, and the inner loop that finds the closest vertex and updates the neighbors. When I say we're going to use this, I mean Project 4. Project 4, you're going to be writing Prim's algorithm. It's going to be a dense graph. Use this one. For a sparse graph, Kruskal's is faster. We talked about using a heap-based Prims, which would be something we could use on a sparse graph. We could also use a sparse graph Kruskal's here. So the sparse graph, heap-based Prims, and Kruskal's both have the same big O. So when it comes down to it, either one of those would probably be okay. If you get into something that needs to have just ultimate top speed performance, then how you implement those two algorithms is going to make a difference. And so you would probably have to implement both of them and see which one actually ends up faster, because they have the same overall big O, the heap-based Prims and the Kruskal's for sparse, both of those for sparse graphs. So you could do either one. I think more often than not, the Kruskal's ends up being faster, because it kind of relies on how efficiently you can sort things and how efficiently you do union find. So there's some tweaks going on in there. But if it comes down to just which one should I use, there's no real good tie break for sparse Prims and a Kruskal's. They're the same big O. They're the same. But if you're going dense, definitely use the nested loop Prims. Here's some things to think about. You're trying desperately to go to sleep. Prove that Kruskal's always finds an MST. Prove that Prim's always finds an MST. Prove that Prim can start anywhere, and then work your way back through some of these things. All right. Stay safe. Dissent, you need to. I'll see you in office hours.